episodes. Will you recommend the Job Guide 360 interview guide to prospective job seekers?
Sure, I will. The guide is detailed and very comprehensive.
Welcome back to the Deep Dive. Today, we are really tackling something critical. We're aiming to give you the ultimate shortcut to mastering the machine learning engineer domain.
That's right. We've dug through a ton of research, basically synthesized everything about the most common technical and behavioral questions asked in MLE interviews all over the world.
Think of this maybe as a kind of a focused curriculum.
Exactly. A curriculum. We're not just listing questions. No. We're extracting the core skills, the knowledge you absolutely need to show you're ready. Practical proficiency.
Right. So if you can confidently handle what we covered today, you're basically ready for the role.
That's the idea. Yeah, you're ready.
Okay, so let's unpack this role first.
Yeah.
Machine learning engineer. People sometimes mix it up with data scientists, don't they? But the sources make a distinction. What's the MLE really responsible for?
Yeah, they do get mixed up. The MLE is fundamentally the engineering muscle. Data scientists might focus more on the theoretical models, the exploration.
The what if.
Kind of, yeah. The MLE designs and implements the robust algorithms, the ones that let computers learn from massive data sets, you know? They build the bridge from theory to reality.
Making it work at scale.
Exactly. High-performance, scalable systems, stuff that handles real-world load. It's all about optimization, deployment, getting it out there.
Okay, and to do that, you need some serious skills. Before we even get into specific algorithms, what are those non-negotiable foundations? What do you absolutely have to bring to the table?
Right, the fundamentals. The research really points to 5 key things, non-negotiable. First, programming. You gotta be good.
Python, I assume?
Oh yeah, Python is king, but also R and often Java, especially for those big production systems. Second, math and stats. A deep understanding.
Okay, hold on there. Linear algebra, calculus. Why is that so critical if you're spending most of your time in Python frameworks, maybe using libraries?
Good question. Because otherwise, you're just running black boxes. You don't really know what's happening. Calculus. That's how you understand optimization. Like how algorithms minimize error, gradient descent, all that.
Okay.
And linear algebra. Well, that's the language of data. How features get represented, transformed, especially neural networks. Knowing this lets you debug, customize, not just import library.
Makes sense.
Oh.
You need to look under the hood.
You really do.
Okay, so we've got programming, math. What else?
Third, data handling skills. This is huge. Preprocessing, cleaning, transformation. It's not glamorous, but honestly, it's like 80% of whether your model works well.
The dirty work.
Totally. Fourth, knowing the frameworks. TensorFlow, PyTorch, scikit-learn, those are the big ones. And finally, something that feels like a soft skill, but it's really not. Top-notch analytical thinking. And being able to adapt, solve problems quickly.
Right, because the field changes so fast. Okay, let's dive into building the model itself, conceptually. That starts with understanding the basic ways machines learn, right? How should someone quickly break down those 3 main learning types?
Yeah, the paradigms. You start with supervised learning. Easiest one. The model learns from labeled data. You give it examples and the right answers.
Learning by example.
Exactly. Then, unsupervised learning, no labels here. The model has to find the hidden structure itself. Patterns, groups. Think clustering.
Finding needles in haystacks without knowing what a needle looks like first.
Sort of, yeah. Good analogy. And the third one, that's more dynamic, involves strategy.
Right, that's reinforcement learning.
Yep. You're training an agent, like a bot or a system, to make decisions. It gets rewards for good moves, penalties for bad ones.
Learning by trial and error, like playing a game.
Precisely. Learning to maximize rewards over time within some environment.
Okay, paradigms understood. Now, picking the right tool. Algorithm selection. What does the research say about how candidates should justify their choices? It's not just picking one at random, is it?
Definitely not. You need to show practical judgment. Understand the trade-offs. So, for instance, if the business needs to know why a model made a decision, interpretability is key.
So you go simple.
You lean towards simpler models, yeah. Decision trees, maybe linear regressions, things you can explain easily.
Simpler often means less powerful, right? What if you just need the best possible prediction? High accuracy on a complex problem.
Then you switch gears, exactly. For top accuracy, you'd probably go for ensemble methods.
Like random forests, gradient boosting.
Those are the ones. They combine lots of weaker models, basically, to get really strong performance. But you have to admit the trade-off. Usually more complexity, harder to explain why it made that specific prediction right away. Black box territory sometimes.
Got it. Trade-offs everywhere. Now, Let's talk about that big danger zone, the one that trips everyone up, overfitting.
Ah, yes! The classic.
Easy concept. But how do experienced candidates talk about preventing it effectively?
Well, overfitting is basically when your model learns the training data too well. It memorizes the noise, the quirks.
So it looks great in training.
Looks amazing, but then falls apart on new data it hasn't seen. Totally useless.
Okay, how do you fight it?
Yeah.
What should candidates mention?
2 core strategies, always. First, cross-validation. Rigorous cross-validation. You need to show the model works well on different slices of your training data that it generalizes.
Make sure it's not just lucky on one particular split.
Exactly. And the second strategy, it's basically about forcing the model to simplify itself, penalizing complexity.
Okay.
That's regularization, specifically L1 and L2 methods. It's really good to explain the difference.
Oh, wow.
L2, ridge, generally keeps all the feature weights small, prevents any single feature from having too much influence. L1, lasso, is interesting. It actually forces the weights of irrelevant features all the way down to 0.
Oh, so it does feature selection automatically.
Yes. Creates sparsity. It's a really powerful side effect, shows you understand the nuances.
Okay, model stabilized, hopefully not overfitting. Next step, checking how well it actually works. Evaluation. Interviewers expect more than just accuracy, right?
Yeah, absolutely. Just saying it's 90% accurate can be super misleading, especially if your data is imbalanced, like trying to detect rare fraud cases.
Right. You could be 99% accurate by just always predicting not fraud.
Precisely. So you must talk about precision, recall, and the F1 score. Precision of the things you predicted positive, how many were actually positive recall. Of all the actual positives, how many did you find?
And F1 is the balance between them.
It's the harmonic mean, yeah. Gives you a single number balancing that trade-off. And you need to mention the tools, too.
Visual tools.
Yeah, like confusion matrices, they break down everything true positives, false negatives, true negatives, and ROC curves.
Right, receiver operating characteristic.
Yeah.
Shows performance across different thresholds.
Exactly. Combine all that metrics, confusion matrix, ROC curve, plus the cross-validation results, and then you have a solid picture of performance and robustness.
Okay, that makes sense. Let's just shift gears a bit. The data pipeline. This is where the engineering part really comes in, isn't it? Starting with feature engineering.
Totally. Feature engineering is, well, it's critical. Garbage in, garbage out, right? Model performance hinges on good features.
So how should someone describe their approach? Is it just intuition?
No, it should be systematic. Start with deep exploratory data analysis, EDA, really understand the data first. Then use techniques like correlation analysis, see what's related, and look at feature important scores from early models.
Using the model to tell you what data it finds useful.
Exactly. It helps you select the best features, or even create new ones by combining or transforming existing ones. It's part art, part science.
But the real world, data is never perfect, is it? It's messy. Missing values are common. How do you handle that?
Yeah, missing data is everywhere. The key is your strategy depends on why it's missing and how much is missing. You can't just do the same thing every time.
So what are the options?
Well, you could do simple stuff like mean or median imputation, fill it in with the average. Or more sophisticated things like KNN imputation. Use the neighboring data points to guess the missing value. Or even
build a model just to predict the missing value.
Yeah, model-based imputation. If it's really important, you need to show you can assess the situation and choose appropriately.
Okay. And maybe the trickiest data problem, imbalanced data sets. You mentioned fraud detection. What's the advanced strategy? You're just listing techniques isn't enough, is it?
No, you need a strategic approach. The best candidates talk about combining techniques. For instance, SMOTI.
SMOBI.
Yeah. It stands for Synthetic Minority Oversampling Technique. You basically create new artificial data points for the rare class, the minority class.
To balance things out.
Right. But you often don't just do SMSD alone.
What do you pair it with?
Often cost-sensitive learning. This means you tell the model, hey, misclassifying one of these rare cases is much worse than misclassifying a common one. You assign a higher penalty.
So you force the model to pay more attention to the important minority class.
Exactly. Using SOTI and cost-sensitive learning together, that shows a really solid practical understanding of tackling imbalance.
That's definitely getting into the advanced details.
Yeah.
Okay, features are engineered, data's clean, maybe balanced. Now we tune the engine, right? Hyperparameter tuning. How does that process work?
Right. Tuning for peak performance. It's optimization again. The standard approach often starts broad, maybe with grid search.
Trying every combination.
Pretty much, yeah, within a range you define. Can be slow, though, so then you might move to random search.
Just picking random combinations.
Yeah, it sounds weird, but it's often more efficient. Samples the parameter space randomly, often finds good results faster than trying everything.
And tools. What should people mention?
You absolutely have to mention the tools. Scikit-learn has utilities for both grid and random search, but even better is mentioning specialized libraries like Optuna.
Optuna, what's special about it?
It uses more advanced techniques like Bayesian optimization. It learns from past trials to make smarter guesses about where the best parameters might be. Much more efficient.
Very cool. Okay, let's make a big leap now. From the lab, the clean environment, to the messy reality of business. MLOps, machine learning operations. First up, reproducibility. How do you make sure your amazing results can actually be replicated?
Yeah, this is fundamental engineering discipline. Reproducibility is everything. The sources really stress systematic solutions here. It means version control, Git.
For code, obviously.
For code, yes, but also for your data.
Yeah.
In your configuration files, everything needed to recreate that result.
I like the analogy of a complex delivery. You need a standard shipping container, right? So everything arrives intact.
That's a great analogy.
Yeah.
And that container is Docker. You absolutely need to talk about containerization. Docker ensures the environment, the OS, the libraries, all the dependencies is exactly the same in production as it was when you trained and tested.
Gets rid of that, well, it works on my machine problem.
Exactly. Eliminates it. Foundational for reliable deployment.
Okay, reproducible. Now we deploy it, get it out there, and keep it running. Talk about that transition to production and the ongoing maintenance.
Right. For deploying at scale, managing all those containers, you should mention orchestrators. Kubernetes is the big one.
K8s.
Yep. But deploying isn't the end. It's really just the beginning in MLOps. The focus immediately shifts to monitoring, constantly.
What are you monitoring?
Performance metrics, obviously. Accuracy, precision, recall, whatever's relevant. But also data drift is the incoming data changing from what the model was trained on. And technical stuff like latency. Is it responding fast enough?
Yeah, when things go wrong.
You need alerts, robust alerting systems. And crucially, automated retraining pipelines. Models degrade over time as the world changes. You need a way to automatically update them with new data before performance drops too much.
This is where real-world experience shines through, right? Troubleshooting.
Yeah.
What are the common pitfalls MLEs need to watch out for?
Two big ones always come up, overfitting, which we talked about, and the other sneaky one is data leakage.
Data leakage. Sounds bad. What is it?
It's when information from outside the training set somehow creeps into the training process. It could be data from the test set or information about the future that the model wouldn't have in reality.
Leads to models looking way better than they actually are.
Exactly. Wildly optimistic results in development, then they crash and burn in production.
The source material had a concrete example of troubleshooting this, didn't it?
Yes, and using examples like that is powerful. A good story would be noticing model performance tanked in production, tracing it back, finding leakage during preprocessing, maybe calculating normalization stats like the mean using the entire data set before splitting into train and test.
Ah, so the training data implicitly knew something about the test data.
Precisely.
Yeah.
The fix. Correct the pipeline. Calculate those stats only on the training set, then apply them to the test set. Retrain. Problem solved. Telling that story shows real, hands-on understanding.
Definitely. Okay, let's shift to a different kind of awareness. Ethics. This is huge now in ML. What's expected?
Non-negotiable. You have to show you're aware of potential bias, systemic bias in data, or baked into the model's assumptions.
And it's not just about awareness, right?
No, you need to discuss how you detect bias, what methods, and what mitigation strategies you could use, fairness metrics, maybe algorithmic adjustments. Plus, you need to talk about transparency, accountability, following ethical guidelines. It's critical.
Absolutely. Okay, final stretch of the interview simulation here. Communication, collaboration. People say soft skills are hard skills in ML. What's the evidence? Why are they so important?
Because they're often the highest leverage skills. Think about it. Effective communication is key, especially talking to non-technical people, product managers, marketing, stakeholders.
Translating the tech speak?
Exactly. Turning complex model outputs into business insights they can actually use. And then there's problem solving, obviously, and just adaptability. This field changes ridiculously fast. You have to keep learning.
That communication skill often gets tested correctly, doesn't it? Like, explain concept X to a non-technical person. What's a good analogy for something complex like a neural network?
Yeah, that's a common test. The research highlights a good one. comparing neural networks to the human brain learning.
How so?
You say, just like our brains strengthen connections between neurons when we learn something new through experience, a neural network adjusts the weights, the connections between its artificial neurons or layers when it sees more data. It learns patterns progressively.
Grounds it in something familiar.
Instantly. Makes it much less intimidating for someone outside the field.
And collaboration. MLEs don't work in a vacuum. How do they stay aligned with data scientists, software engineers, product folks?
It comes down to clear, consistent communication. Using shared tools helps Slack for chat, Jira for tracking issues and progress. But it's also about proactively seeking feedback, making sure everyone understands what the model does, what data it needs, what its limitations are. No surprises.
Right. Okay, before we get to the final preparation tips, let's quickly hit 2 advanced topics that show you're really up to date. Transfer learning and cloud platforms. Briefly, what are they?
Sure. Transfer learning is super efficient. You take a big model that's already been trained on a massive data set for a general task like image recognition on ImageNet,
Okay.
and then you adapt it, fine-tune it for a new but related task, maybe classifying specific types of medical images. You leverage the prior learning, saves a ton of time and data.
Smart reuse.
Yeah.
And cloud platforms.
Interviewers expect you to know the main ones: AWS SageMaker, Google Cloud's AI platform, Azure Machine Learning. You need some familiarity, maybe specific experience, because these platforms streamline the whole workflow development, training, deployment, monitoring, everything we've been talking about.
Makes sense. They're the standard environments now.
Oh.
Okay, so imagine you've nailed all the technical questions. You've shown your skills. Now the tables turn. You get to ask them questions. What should a candidate ask to gauge the company's maturity and if it's a good fit?
This is crucial. Your questions show what you value. The sources highlight 4 really good ones. First, how does your team currently handle model deployment and monitoring in production?
Checks their MLOps maturity, like we discussed.
Exactly. Second, can you describe a recent challenging project the team faced and how you overcame the obstacles? Shows their problem-solving culture, how they handle setbacks.
Good one. And the last 2, more about the role and responsibility.
Yep. Third, what opportunities are available here for continuous learning and professional development? Shows you're serious about growth in this fast-moving field. And fourth, circling back to ethics, how does the team ensure the ethical and transparent use of ML models in practice? Reinforces that critical awareness.
Those are excellent questions. Okay, let's wrap up with final advice, preparation. What's the ultimate summary for you, the listener?
Okay, key takeaways. Master those core algorithms and concepts. Don't just memorize, understand the why, the trade-offs. Critically, get hands-on experience. Work on real-world, end-to-end projects. That lets you give those concrete troubleshooting examples we talked about.
Builds that practical credibility.
Absolutely. And finally, you just have to stay updated. This field moves incredibly fast. Follow the key research journals, like ARCs, maybe IEI publications. Attend webinars, take online courses, engage with the AI community online. Constant learning.
It really sounds like a blend, doesn't it? Mastering this role is about deep technical skill, understand generalization, tuning, deployment, but also those crucial soft skills. Explaining complexity, collaborating effectively.
It really is that balance.
Yeah.
And, you know, that point about staying updated, reading journals, it brings up a final thought. Yeah. In a field evolving this quickly, with new papers dropping daily on RxC, how do you, as a practitioner, decide which of these brand new advancements, these complex new models or techniques, are actually worth investing the time to learn before they become the next standard interview question? Where do you draw the line between cutting-edge research and practical need-to-know skills right now?
That's a tough one. Definitely something to think about as you prepare for that next big ML engineer role. Thanks for diving deep with us today.